Okay, for those of you who are interested, this is the full-blown details of all the code in this Sudoku solver. Completely unnecessary for the assignment, but some of you are obviously kind of going above and beyond and really curious about all the little details. And so I feel like for those of you who are interested, I really want to provide you with everything that I can to satisfy your curiosities. So here we go. The solve class. It extends JFrame, and you've, I'm sure, noticed that anything that has its own Java window for our class is going to extend JFrame. Now, there may be other ways to do it, but this is the way we do it. Implements runnable. So the only reason for this is because I wanted to display sort of an animated video that gives a little more insight as to what it's doing while it solves, rather than just immediately displaying a solved puzzle. So I have modified this a little bit, and if I now pick a puzzle, you get to see it's going through and trying to solve it. In order to have this sort of animation, I had to implement runnable so that I could have an update loop and have it repaint after various portions of the algorithm. And what you're seeing here in this animated video is that it is starting with the first puzzle. It guesses and reduces, and the blue squares are the places where it's found invalid solutions. And it goes back to the original and starts guessing again. And it keeps on doing this, guessing and reducing until it either finds an invalid and then going back and guessing and reducing again until eventually it gets a bunch of lucky guesses and ends up with a solved puzzle. And you can see with the animation, sometimes it might take quite a while. It does an awful lot of guessing before it finally gets a solved puzzle, but it does eventually get a solved puzzle. And because computers are so fast, all that wrong guessing is quite acceptable. Without the delays in animation, it'll go through that in just a split second. So then serial version ID is just because whenever you extend JFrame, it'll give you a warning if you don't add this. And so that's just to get rid of a warning. Public static final int height, that's the height of our window. The int width is the width of our window. And board, I've got both main and temp. Main is the main board that we get when we originally open the file, and temp is going to be the one we're working with as we're making our random guesses. And if temp ever becomes invalid, we just discard it and then make another clone of main. Buffered image off screen, this is just a little double buffering so that we can get our animation to look a little bit better and reduce flickering on the screen. Solve, this is the constructor. This is what creates the instance of the JFrame, the instance of the whole application. This is what's going to be displayed on our window. So we start out just setting temp to null. We don't store anything in temp right off the bat. We create a file dialog box and set the file dialog box to point. What this does is this sets the file dialog box so that when it opens, it will default to the same folder as our project. And I have noticed that this behaves slightly differently in different operating systems, but it's usually a good idea to tell the file dialog box what folder to start in. Otherwise, the person has to sit there and browse forever. Set it visible. That makes the file dialog box show up. And then once they select the file and hit OK, it disappears. Then new board, this calls the constructor of the board class, and it returns a board. And it gives it, so we call it getFile. This will return, the getFile method on a file dialog box will return the file that the person selected before they hit OK. Off-screen, this is just initializing the off-screen image, the thing that is used for double buffering just to reduce flicker. This initializes that variable to be an image that is the same size as our window. New thread, start. So if you implement runnable, you can do a line of code like this that will start a separate thread of execution. And this is useful when you're doing some sort of animation. And because I wanted to do an animated display of the algorithm, I used this so that I could create a separate method. So you implement runnable, and then in the constructor you say new thread this.start. That will start your run method. So when you implement runnable, you have to write a run method, and this will start that run method in a separate thread. And so down here, I've implemented a run method. And that run method has the algorithm for solving the puzzle. Paint, that's to display something on the screen. So I want to draw everything on that off-screen image first, and then when all my drawing is complete, I just put that off-screen image on the screen. That's how double buffering works. And so first, if I want to draw on the off-screen image, I have to get its graphics object. So get graphics from the off-screen image, and then set the color of that graphics to white because I want to clear the background. Fill rectangle, 0, 0, this width, this height. That just clears the whole background to white. And then if temp is not equal to null, tell temp to paint. Temp is a board. And so we just tell the board to paint itself off screen. Otherwise, we tell main to paint. So if we're in the middle of the algorithm, temp is going to be equal to, well, in the very beginning of the program, temp is equal to null. And this just keeps that from crashing. After the first iteration of our algorithm, temp is going to be equal to, well, the clone of board that we're currently working on. And so we just go ahead and paint main to begin with. And then this draws the off-screen image on the screen. Sleep. This is just a little helper method. I give it a duration that tells the thing how long to pause, and it says thread sleep, that duration. That is a duration in milliseconds. So if that duration is 1,000, the program will pause for 1 second. And whenever you tell a thread to sleep, that may crash for some reason. So you've got to catch. It may be interrupted. The sleep may be interrupted. And so you've got to catch that interrupt. And then you tell it to repaint. This is just for the animation. I could have put the thread sleep and repaint right in the run method, but I really didn't want to have to retype this try catch and clutter it up. So it was just a way of taking these 5 or 6 lines of code, compressing them down to one simple line of code that I could put several places inside of the run method. So the only thing left to explain is the run method. So we start out just by sleeping a half second. And so in the constructor for main, we created a new board, and it should probably display that board for a half second before it does anything. There you go, that half second. It goes by real quick, but it showed all the samples. Got lucky that time, it ended quickly. Then reduce main, Boolean solved. We start out saying, hey, this thing is not solved, and this count equals 0. I'm going to count how many times I make guesses, and if I guess too many times, then I'm going to say this thing is unsolvable. If I guess 100,000 times and I still haven't solved it, I'm just going to set solved to true, temp equals null, and print out some text that there's no solution. It is extremely unlikely that I will have to guess 100,000 times. We will almost always get the right solution in fewer than 1,000 guesses. Even just 1,000 guesses, we've got like a 1 in 1,000 chance of not getting the solution after 1,000 guesses. And 100,000, oh, you're probably more likely to get struck by lightning 3 times in the same day than to guess incorrectly 100,000 times and still not get the right solution. So at this point, if we've guessed that many times and still don't have a solution, it's pretty safe to say that no solution exists. So as long as it's not solved, sleep. So this allows it to display a little bit what we currently have thus far in the algorithm for 200 milliseconds. Create a new board, main, so this is creating a clone. You notice that I've got a constructor for a board that takes a board. That is called a clone constructor. It creates a deep copy of that board. There is a difference between a deep copy and a shallow copy, and what we want is a deep copy. And so that's going to copy the board, and we'll see where I wrote that when we look at the board class. Once we've made a deep copy, since main is always valid, we never destroy main. We never make a guess on main. So it is always valid. The only thing that makes something invalid is if we make some sort of a random guess. So we make that deep copy and we set valid equal to true, and we increase the count because we have just made a clone. Each time we make a clone, meaning that we reached an invalid state, we're going to increase that count a little bit. As long as this thing is valid and not solved. Okay, so if it becomes invalid, we get out of the loop. If it becomes solved, we also get out of the loop. So if it's solved, we exit this loop, and then we come back around and exit the other loop, and we're all done. But if it just becomes invalid, we'll exit the inner loop and come back around and do the outer loop again, and then go back into the inner loop with a brand new clone. This just prints the count. This helps me keep track of how big that count got. And when I was testing this, I put the whole thing into a loop and made it solve 1,000 times, printing out the count every time, and just watched to see how big that count got on average. And the average count was, about 100. And after solving it 1,000 times, the count never got to bigger than 1,000. And I did that a few times, and I never ever saw a count bigger than 1,000. So I felt that it was safe to quit if I ever got a count to 100,000. So if out of 1,000 times we never see a count of even 1,000, the probability of getting a count of 100,000 is almost nothing. Then we sleep for just 5 milliseconds. This just allows us to see that invalid puzzle, or a puzzle that has been had some random guess and then reduced, but not quite solved, and not a clone of main. So then we make a random guess and we reduce it. And then we check to see if it's solved. So this is calling the isSolved method of the board that is stored in temp. And then this calls the isValid method of the board that is stored in temp. So now we know if temp is currently solved or valid, and we can come back around in the loop. And this checks to see if the count is bigger than 100,000. If it is, we go ahead and set solved to true just so that we can get out of the loop. We set temp to null because temp would have been it's at this point still invalid. And then if temp is not equal to null, we set main equal to temp. So at this point, we have never changed main. Main is the original puzzle after that first reduce. If temp is not null, then we must have exited because it was solved and not because our count got so high. So if it's not null, then we're just going to replace main with temp, that solved puzzle, and then repaint the screen, displaying that new solved puzzle. If temp is null at this point, when we repaint, it's going to show main, the original puzzle. So let's look at the board and all the dirty code inside of board. So a lot of fancy details. And everything else before, I've only really talked about the mySquares variable, the two-dimensional array of squares inside of board. I've created a couple of other things, this horizontal offset and vertical offset. So when I draw this thing on the screen, I used a couple of variables to control the way it was displaying. So you'll notice that there's a little bit of room in the upper left-hand corner and in the lower right-hand and bottom corner. And these offsets control how much is in the upper left-hand corner. It shoves the puzzle down a little bit so that we've got a little clean space. So inside of the solve class, we've got a height and width that controls the size of the whole window. Inside of the board class, that controls the offset of the board from in the upper left-hand corner. In the constructor of a board, we've got two constructors, one that would take a file name and the other one that would take another board. This one that takes another board, that's the one that does a clone. So it needs to create a new array of squares and then fill them up with copies of the squares that were inside of this other board. And so now I've created a clone constructor for square that takes a square and makes a deep copy of a square. So first we create a brand new array of squares, and then we go through in a loop, we clone each of the squares inside of the board we were given and take those clones of the squares, not just references to the squares that were in B, but clones of those squares, deep copies of them, and stick it into our brand new array. So it's a deep, deep copy. If we get a file, if that file is null, just quit. Okay, so this is a little bit tricky. If we fail to open a file, the program is probably just going to crash. But this just causes it to quit early. If they hit cancel without selecting a file, it's not even going to try to do the rest of this stuff. So then it's going to create a new empty array of squares, and then it's going to create a buffered reader. A buffered reader from a file. So in order to create a buffered reader so that you can read from a file, you have to first create a file reader, and from that file reader create a buffered reader, and I assigned it to a variable in. And then we go through a loop. For 9 rows, we read one line from the input file, in.readLine, and we convert it to an array of characters. Okay, so when you do in.readLine, that gives us a string, and if you use the 2-character array method of a string, it'll convert it to an array of characters. That makes it easier for us to get those characters out of the array one by one. And so if you look at one of these input files, that line is going to have 3 spaces. Those are the first 3 characters. The 4th character is the vertical bar. 3 more characters, another vertical bar, and then 3 more characters. So in.readLine, the first time you call it, you get this first line of text. And we're going to turn it into an array of characters. The next time you call in.readLine, it'll give you the next line of the input file. And then the next time you call it, you'll get the next line, and the next time you call it, you get the next line, and so on. So for 9 rows, you're going to read a line and convert it to an array of characters. And then for int I equals 0, c equals 0, c less than 9. So we're going to go through each of the columns, c++ and I++. If that character, if line sub I is equal to a vertical bar, just add 1 to I. Skip over the vertical bars. And then set my square sub RC to some new square, giving it the appropriate character from the line. So we're going to create a square from a character, a single character of the input file. If r plus 1 mod 3 equals 0, this is what allows us to skip these horizontal lines in the input file. So we're going to read through the first 3 lines and then skip one, and then read through 3 more and then skip another one. So this gives us a skip. So r plus 1 mod 3. So 0 plus 1 is 1. When you divide it by 3, the remainder is 1, not equal to 0. So when r is 0, we don't skip a line. When it's a 1, we don't skip a line. When it's a 2, we're going to read the line, process it, and then skip a line. We read and throw away the line. After we process line 0, 1, and 2, we're going to skip a line. So after we process line 0, 1, and 2, after we've processed all 3 of those, then we're going to read this line in, and then come back around and read in another line without processing the one that we read here. So when r is 2, r plus 1 is 3. 3 divided by 3 has a remainder equal to 0. So that's what allows us to skip the line, the third line. And then we're going to process 3 more lines and then skip a line again. So this is a little trick. If you want to do something, say, every 3rd time through the loop, you do a mod 3 equals 0, and that'll skip a line. We close our input file, and then whenever we try to create this buffered reader that opens a file, we have to catch an exception because that file may not exist. It may fail to open the file, something like that. So you've got to surround this whole thing in a try-catch loop. So that's the constructor of a board that comes from a file, and the copy constructor for a board. Reduce. We start out saying done reducing is false, and then as long as we're not done reducing, set done reducing to true. Okay, so that's a little confusing. So this is setting a flag to false, we set it to true, and then if in the process of reducing this thing, we find out that a square gets solved, then we set done reducing to false again. So if we get through all of this reducing and we never set it to false, then it's going to get out of the loop. That means that in this reducing process, we never solved a square. However, if we do solve a square, it's going to set done reducing to false, and so it comes back around again in the loop, and it keeps on trying to reduce. So as long as it keeps solving squares, it'll keep trying to reduce. But if it ever goes through this entire process and doesn't solve a square, it's gonna say, hey, I've reduced this thing as much as I possibly can. So we're going to go through all the rows and all the columns, and if the square is solved and it has never yet been reduced, so if we reduce on a square once, we're not going to bother reducing on it again. So the idea is it just became solved. Okay? So if a square just became solved, you're going to reduce on its columns. So we're going to call column reduce. On the column of that square, and we're going to row reduce on the row of that square, and then we're going to group reduce on the row and column of that square. And so we're going to reduce in the column, the row, and the group. Each one of these methods, if it solves a square in the process of doing its reduction, it'll return true and set done reducing to false. Once we have reduced on the column, the row, and the group of a particular square, we just set reduced. That says, for this particular square, it has been reduced. Once we have called set reduce on that square, get reduce will return true, and we'll never reduce on that square again. So reduce group, how does that work? We receive a row and a column and a square. So we start out by saying solve the square is false. We have not yet solved the square. If in this process we ever solve a square, we'll set solve the square to true. And then we return whatever solve the square is. Now this is a little bit tricky. First we divide row by 3 and multiply it by 3. And at a glance, this may seem like it does nothing. However, R is an int, not a double. If this was a double, it would, well, aside from giving you a little bit of rounding error, if it was a double, it wouldn't do much. However, because it is an int, it's going to do a lot. When you divide an int by 3, you're going to have some sort of remainder that is thrown away. Let me draw a picture of what's going on here. Okay, so the idea, when I reduce a group, say I've got this cell right here. It is in row 3, column 4. What I'd like to do is I would like to check all of these 9 squares that are in its group. What I'd like to do is I'd like to start with this upper left-hand corner square and then go through the 3 different rows and the 3 different columns. However, I don't necessarily have the index of the thing in its upper left-hand corner. So if I take the index of this cell where I've put the X, if I take its row and I divide it by 3, its row is 3, divide 3 by 3, because it's an integer, I get 1. Okay? And then I multiply it by 3, and I get 3 again. If I take its column, 4, and I divide 4 by 3, I would have 1 with a remainder of 1, but because it's integer arithmetic, I get 1. It throws away the remainder. Multiplying by 3 again, so 4 divided by 3 times 3. First I take the 4, divide it by 3. This gives me 1, multiply it by 3, and I've got 3, not 4. I don't end up with what I've started. If I have 5, 5 divided by 3 is 1 with a remainder of 2. I lose the remainder. And when I multiply it by 3, I come back to 3 again. So if I've got a 3, a 4, or a 5, I divide it by 3 and multiply it by 3, I end up with a 3. If I've got a 6, a 7, or an 8, well, 6 divided by 3 is 2, multiplied by 3 is a 6. 7 divided by 3 is a 2, multiplied by 3 is also a 6. And 8 divided by 3 is a 2, because I'm throwing away the remainder. And then multiplied by 3 is also a 6. So this is a tricky little thing. What I end up with, essentially, is the coordinate of the cell that is in the upper left-hand corner of that particular group. So no matter which row or column I give it, I'm ending up with, after I execute this code that divides by 3 and multiplies by 3, this R and C is no longer the row and column of the square. It is now the row and column of the square that is in the upper left-hand corner of S's group. So now x equals 0, x less than 3, x plus plus. Y equals 0, y less than 3, y plus plus. This is an offset. So now I'm going to find the square at r plus x, or r plus y and c plus x. So I'm going to say 3 plus 0, 3 plus 1, 3 plus 2 for each of the columns and each of the rows. And so this will visit each one of the squares in the group, in the same group as square S. If that square is not equal to s. It's very important because I want to skip over the 1 for s, and I want to say if it is solved. Okay, so temp stores whether or not this thing is solved. If it is, well, I'm just going to call remove, whether it's solved or not. I'm going to remove the solution that was in square s. Remember, s was solved, right? And so I get its solution, and I remove that solution from this square. So I'm removing, so say this one is solved. If I visit all of the squares in its group, skipping this square and remove the solution for this square from each one of those squares, that's how I reduce that group. Now, I knew whether that square was solved before I removed the one solution, right? Now, if it was already solved and you know, saying, you know, maybe this value, say this square was already solved and it held a 5, and this one is solved and it's holding a 2. If I try to remove 2 from here, well, a 2 isn't in its list of possibilities. It won't really have any effect at all. Well, that's fine. But if it had a 2 as a possibility, if it had both a 2 and a 5 as a possibility, removing that 2 will make it solved. So I stored whether it was solved or not. If it had a 2 and a 5 as a possibility, it was not solved. I remove one of those, it is now solved. So if it was not solved before and it is solved now, then we have just solved a square. We set solved a square to true. And so this goes through each of the squares in the group, skipping the one that we're reducing on, and it removes the solution of this square from all the other squares in that same group. And if any of them becomes solved, we'll return true, we've solved a square. Reduced column is similar, except instead of going through every thing in the column, it's going to go through each row of that particular column. It's a little bit easier. So I give it a column and we give it a square. So this C is the column that this square is in. Now for each row in that column, if the square that we're visiting is not equal to S, then if the square we're visiting is solved, we store the fact that it's solved. We reduce the solution. We take the solution for S and remove it from all the other squares in that column. If a square was not solved before and it is solved afterwards, then we have solved the square. If any one of those squares was solved, then we return the fact that we have solved a square. Reduce row, it's similar. We start solved a square out as false for each column in this row. If this square in that row and column is not the square we're reducing on, then we'll store the fact of whether or not it is already solved. We remove the solution for S from that square. If it was not solved before and it is solved now, then solved the square is equal to true, and we return the fact that we have solved a square. So that reduces rows, columns, and groups. If at any point in any of those three reductions it solves a square, then it keeps on trying to reduce. For paint, sets the color to black. If the thickness, and it's going to go through and it's going to draw 9 lines. If I is equal to 0, 3, 6, or 9, it's going to set the thickness to 6. Otherwise, it sets it to 3. So this is a tricky little bit of line of code. This is called the ternary operator. The first expression is either true or false. If I mod 3 equals 0, and the question mark says, hey, if this first part evaluates to true, then the whole expression will evaluate to whatever comes before the colon. Otherwise, it will evaluate to the thing after the colon. So if I is equal to 0, 3, 6, or 9, then the thickness is going to be 6. Otherwise, it's going to be 3. That is what allows us, when we run this thing, to have thick lines at 0, 3, 6, and 9, but thin lines everywhere else. It just makes the thing a little bit prettier. Fills a rectangle. That is, so there's a horizontal rectangle and a vertical rectangle for the horizontal and vertical bars. So if it's a, the first two parameters are the x, y locations of the bar. We're going to use the vertical offset for the y value. If it's a horizontal bar, no, if it's a vertical bar. If it's a vertical bar, v offset is the y value. And I times the width of a square plus the offset is going to be the x value. It's going to have a thickness in the x direction, and it's going to have a thickness in the y direction. The thickness in the y direction for vertical bar is 9 times the square height, plus 6 is just to make it look a little pretty. And if you understand all of that for drawing the vertical bars, you'll be able to figure out this for drawing the horizontal bars. So this just draws some black horizontal and vertical bars for our grid. And then for each of the rows and columns, we tell the squares to paint themselves. Given a graphics object, tell it, when we tell the squares to paint themselves, we tell them what row and column they're on. Because I didn't store a variable inside of the square. It doesn't, each square does not know what row and column it's in. So it's going to use, the paint method is going to use that information passed to it so that the square will know where on the screen to paint itself. So this draws each, it draws the grid and then it draws each one of the squares. And those methods at the bottom, these methods at the bottom are the ones that you're supposed to write. Okay, the square method. A square has a list of possibilities. Now you'll notice that I've made some variables, public, static, final. What does that mean? Well, every square is going to have exactly the same width. So I didn't really need to store the width individually for each square. So I made it static. Static means it belongs to the class rather than belonging to an instance of the class. It means that it's going to be the same for every instance of the class. And so anything that is the same for all instances of the class, I can just make static. I've done that with the width and height of an individual square. I've done that with the width and height of the full application. And I've done that with the offsets of a board. Any of one of these things is going to be the same for each and every board that I create, for each and every square that I create, for each and every application that I create. So I just go ahead and make it static. And because it never changes, I'm just going to make it final. Font. Okay, so you'll notice that when we run the application, I've given it a little bit of a pretty text. And so to do that, I need to create a new font. Color. When I run the application and doing the animation of the algorithm, you'll notice that I did a blue square when it was invalid. And so I went ahead and added a little variable where it would store the color. Oh no, I'm sorry, that's the color of the text. So the color of the text is red if it started out as solved. And so if we pass in a character in the constructor, it's going to set the font color to red. That's why all of the things that are initialized from the file are red, and the ones that the algorithm solves are black. And we need to be able to store the color of each square individually. Boolean reduced. That's the flag that we set to true once we reduce on a square. That's just for efficiency, so we don't end up reducing on the same solved square multiple times. So you'll remember in the board, when we were reading the file, we created squares from a character. Okay, so this is the constructor that does that. It sets reduced to false. Whenever we first create a square, we haven't yet reduced on this square, so we start reduced out to false. If my font equals null. So you'll notice that font is static. All the squares are going to have exactly the same font. I didn't make it final because I couldn't actually create the font outside of the constructor. Because I needed to open a file and do some other stuff that you just can't do outside the class. So I did this, I wanted to only do it one time, not every time that I create a square. So if you declare an object outside of the constructor and you don't initialize it, that object is set to null. So then the first time I create a square, it's going to be null. I'm going to go ahead and initialize it. But because it's static, once it's set to something other than null, then the next time I create a square, it's already initialized. The second call to a square constructor is going to see that the font has already been initialized, and then this is not going to be equal to null, and it won't bother initializing it a second time. So this is a complicated little line of code that is used if I want to create a fancy font. So if you're not familiar with TrueType fonts, if you go to Google and you just type in TrueType font or TTF download, you're going to see a bunch of websites where people have posted special fonts that look really cool that you can download a file that is a .ttf file and store it. The one that I used was Pacifico. And so I clicked on download. That gave me a zip file. When I unzip it, there's a file, a .ttf file, that I included in my project. So now if we look inside of Eclipse, you're going to see this Pacifico.ttf file. So if you use the browser, you're going to find that I've stuffed that file. I downloaded it from the internet, and then I stuck it in the same folder as the project so that I could load it when I create a square and set this font. And if I wanted that font, if I wanted the text to look differently, I could have used any other TTF file that I could find off of the internet. So first, I create a new file, giving it the file name, and this has to be a file that I have saved somewhere in my project folder. And then I create a font. I say font.createFont. I give it the font type. I give it the file that I've opened. And then if from this new font that I've created, I say .deriveFont, and I give it a size. This tells it how big that font has got to be. And so this is Pacifico and size of 50. And I just played with it a little bit with different sizes and different font files until I got something that I thought looked nice. So this is how I get fancy looking fonts in my application. I initialize possibilities to some new empty array of integers, array list of integers. And then if the character that we passed in was equal to a space, remember in my input file, spaces indicated that I have any of the possibilities, but if it was not a space, then it would have been a number, indicating what number should be in that square. So if it was a space, I set the color to black, meaning this is something that my program has to solve. And then for I equals 1, I less than 10, I plus plus, I add I to the possibilities. So this adds the numbers 1 through 9 to the list of possibilities. Otherwise, so meaning if that character was not a space, then it has got to be the character 1, 2, 3, 4, 5, 6, 7, 8, or 9. I set the color to red. Now, characters are stored as a number, and they're all in sequence. So if I go to Google, and I type in ASCII, oh, and ASCII table. So images for ASCII table. I want to look at one of these big. There's lots and lots of them. That's probably not an easy one to look at. Blah. This is a good one. Okay, so these are the different characters. And this decimal number is the number that represents that character. In binary, this is the set of ones and zeros that it would store. Notice it's 8 ones and zeros. 1, 2, 3, 4, 5, 6, 7, 8 ones and zeros. That's 1 byte to store a single character, or 8 bits. And those ones and zeros, they could represent a number 0 to 255. They're only showing the first 127 here. But there are 255 possibilities. And so each character that you can type on your keyboard has a number associated with it. Now, if I look at the numbers 0 through 9, they're all in order. A 0 is a 48, a 1 is a 49, a 2 is a 50. Yeah, it's strange that the 0 character, if I turn it into a number, would be the number 48. So this is how I store a 48. It's also how I store the character 0. So if I have the character 1 and I subtract the character 0 from it, that's 49 minus 48. That gives me the number 1. So if I want to turn a character into a number, if I've got an individual digit character, I can do that just by subtracting the character 0 from the other character. And so if that character is a 1, this will evaluate to the number 1. If that character is 2, it'll evaluate to the number 2, and on up through 9. And so I'm going to add the appropriate character to my list of possibilities. It's only adding 1 character because if I've only got 1 possibility, I'm considering it solved. And so that's a tricky little bit of code that initializes a square to either a list of all the possibilities or the 1 possibility that I wanted from a character that I read from a text file. Set reduce just sets reduced to true. I'm going to do that after I reduce on a square. Get reduced tells me whether or not I have reduced the square. So this is that copy constructor if I want a deep copy of a square. So I have to copy whether or not the square is reduced. I basically have to copy every instance value. I'm going to copy the color. I'm going to copy, I create a brand new array list of possibilities. And then I fill that brand new array list because an array list is an object. And whenever I want to copy the object. I don't want a shallow copy of that array list. Just like I didn't want a shallow copy of the square, I didn't want a shallow copy of the board. So I have to create a new array list and then copy all of the objects from that array list. Now, I can treat the integers as if they were a basic data type for our purposes, because we're not doing any modifications of those integer objects. But because we are modifying this possibilities array, we need to make sure we do a deep copy of the array. So it's a deep, deep copy, but it's not a deep, deep, deep copy, if that makes any sense to you. So for each integer, in this square's list of possibilities, go ahead and add those integers to the array list of possibilities for the new one. Paint. So we get a graphics object that we're going to use to paint with. We have a row and a column that this square is that tells this square where on the screen to paint itself. It sets the color appropriately. It creates X and Y offsets given its height, the board's vertical and horizontal offset, and the row and column that this square is in. If possibilities size is equal to 0, meaning this is an invalid square, it sets the color of the graphics object to a translucent blue. 0 for the red, 0 for the green, 1 for the blue. So this is blue, and then alpha value of 0.5, so it's a little translucent, a little bit transparent. So dip your paintbrush in a little bit of transparent blue, and then fill a rectangle of the appropriate width and height in the appropriate location. So this is what draws the square blue if it is invalid. Create an empty string. If this square is solved, set the font and add a little bit. So this is a little bit tricky. This is going to draw big text if it is solved, but otherwise it's going to draw the solve with a font of 15 instead of a font of 50. And this gives you a little bit of offset, because if it's a small font, we want to have the font shifted just a little bit to the left or right. This kind of centers the font in the square based on its size. So I've got two different shifts for centering based on the size of the font. And then we're going to create this string of all the possibilities. So this is a little bit tricky. So we add, for each of the possibilities, we add the possibility to the square, but we want to draw these possibilities on 3 separate lines. So if we have gone through and already drawn added 3 possibilities to the string, then we go ahead and draw the string and reset it to empty. And then we move down a little bit in the Y. So this draws all the possibilities, and it's not going to draw the last string, so we have to draw that outside the loop. That's a tricky paint method. I've got a lot of tricky code there. I've tried to make the methods that you have to implement maybe not so tricky. And then the last one, is solved, is valid, remove I, get solution, and random guess. Those are all things that you would need to implement. So that's all the gory details that you don't really have to know, but you might find interesting of the Sudoku solver application. I hope that someone has watched the video through to the end. If you have gotten to the end of this video, you didn't get bored and shut it off, I would like to give you a little extra credit. So send me a Canvas message saying, hey, I watched the video to the end, give me my extra credit, and I'll add a little extra credit to your grade. Thank you for watching. Have fun, and yeah, if you have any questions, send me a Canvas message. Thanks.